So in this video, we're going to get into our new topic, our next vulnerability, or next bug here, and that is a buffer overflow. So in the common weakness and enumeration top 25, this is actually number 1 and has a very, very, very large score. The thing with buffer overflows is you can really do a lot with them. They often can lead to arbitrary execution, so attackers can really make the computer do whatever they want if a buffer overflow is present. That's a common result of buffer overflows. Buffer overflows are actually additionally fairly frequent, which is a problem. So hopefully by the end of this video, you'll be able to understand what a buffer overflow is, how to identify a buffer overflow, and how to fix it so we don't have any of these vulnerabilities present in our code or programs. So what is a buffer overflow? Well, kind of as the name suggests, you overflow a buffer, and that's kind of all there is to it. But we need to actually understand that, how that is, and let's get a little bit deeper in here. So within a buffer overflow, what happens is that the data is written beyond the bounds of an object. So for an example, if I have an array that should be of size 10, and I try and write 40 elements to that array, so if I have array square bracket 1, 2, 3, and 4, those are normal locations. But if I try to write to array square bracket 23, for example, that's outside of the bounds of that 10 element array. And in some languages, you'll actually be able to do it. And that can lead to issues. And I'll explain exactly why. This overflow can lead to issues, specifically, in many cases, a program crash. When it leads to a program crash, it's very possible that it actually could lead to execution. So the attacker could actually take advantage of this again and kind of make the computer do whatever it is that they want to do. So this is definitely an exploitable vulnerability. So what languages are you going to see this in? You'll see this, or can see this, in really every language, but by and large, you're going to see it in low-level languages like C and C++, especially in C. Now, everyone should be familiar with C, and we'll look at some C code with this, but C is a very, very low-level language. It gives you direct access to memory. And it doesn't necessarily have a whole lot of inherent protections in place to prevent against some things like this, which in some cases is good if we need that direct unfettered memory access. In some cases, not as much. Our compilers in C don't really care about buffer overflows either, and it's not something that they're necessarily going to pick up on or prevent. Some compilers might help with it. C++ compilers are a little bit more strict, so they might identify some of this happening and prevent it from happening, but C definitely does not. Some of the newer higher level languages, Python as an example, abstract memory access, so it's a little bit more difficult for you to get access to the memory if you need it, but it does have a benefit that overflows are definitely less likely if you don't have that low level access. But if you need that low-level access, the language either will not be sufficient or the performance of that language just might not be good. Any older language is particularly vulnerable to a buffer overflow. So to understand why buffer overflows are bad, we need to learn about this thing called the stack. Now, there's a number of different contexts in which we'll talk about a stack in computer science. A stack can be a data structure that you use to hold data in your program, and there actually is a thing on the computer called the call stack, or the execution stack, or the program stack, right? I'm just going to refer to it as the stack. Now, with what the stack does is it does store information for us, particularly local variables and parameters that are passed into the function. But it also keeps track of program execution. So after this routine, after this operation, this function is done, what should the computer do next, right? Which part of the program do I need to run next? And that's kept track of on the stack using very specific memory addresses. If we're able to mess with that pointer, the thing that says, hey, go here in the program next and run this code, that is really the key component that makes this extremely dangerous if this is actually able to be exploited. So the stack is going to store local variables, things that are within the active routine, the function that you're working on, and all of those disappear after that routine is finished. So that stack gets cleaned up. Those local variables go away. There's no space for them anymore because we don't need them. The stack also will hold past parameters. So if you pass a parameter into a function, it will hold those. So kind of those three major things is what you're going to see on the stack. And the diagram on the right hand side here, you're going to see in many subsequent slides. That is going to be the stack. That's all I'll refer to as the stack, and that's how I'll draw it out here. So we'll have arguments pushed to the stack. So any number of arguments that are arguments to the current routine. They can be different types, different sizes. You could see integers there. You could see arrays there and the like. You're going to have a return address in there where the program is actually going to go to start running after this routine is done. And then any local variable will be declared, and actually space will be available for it on the stack. Right. Again, that's going to be different types, different sizes, whatever those local variables are. You could see chars, you could see integers, and you should know about the sizes of all of those. All of those do get different space allocated for them. So I have an example here just of how this works normally. If I have this function called doMath, I have two parameters that are passed into that function, a and b, at the very top, int a and int b. Those parameters are pushed to the function, and they sit at the very in the stack there, right? So you can see a and b are there. There's also the return address on the stack, which is what this return at the very bottom here is going to do, where that's going to go once I hit that line. So once I hit that line of code, what do I need to execute now? It's probably back in the function that called this one, that called doMath in this example. But that return address is key because that's pointing to wherever the execution is going to be next. And then on the stack, I also see sum and diff, and these are two local variables, two things that are inside of this function here, right? So sum is a plus b. The registers will take this value, combine them and store them in this value here, in that space on the stack. Same thing with diff, and then it will, execute the function. But this is where these things are stored on the stack. It's important to know that because it's important to see if we overflow something, how that actually works. So I have another example, and this example is a lot smaller. I don't have any parameters into this function, but I do have a local variable called words, and words is a 10 character array. So 10 different characters, and I'll just say it'll take 10 different slots up on my stack here. So I have words from 0 to 9. That's the 10 characters there. Now, also I have that return address on the top, right? That return address is just going to point to some place in memory. So I have some random address in there just to illustrate, but there's something there. And words, we could say there's nothing there. Now, if I do a scanf %s words, and I read in something from the user, and I store that into words, that's going to be placed on the stack, right? So if I entered, actually, I'm going to go ahead and program this out a little bit and see if we can kind of see it in action. Let's go here. I'll call it test. So I have my oops function here. Again, all it's going to do is make this words array of size 10 and then read in from the user %s just something into words. That's all it's going to do. I could print it out here. I'll do that just for fun. Printf %s, let's do a /n and words. So I'll print that out. I'm going to open up another terminal here so we can kind of do this side by side. I am on the desktop. Test.c. Oh no. I have not actually programmed on this machine before, and I need to install this. All right, so we'll pause briefly until that gets installed. CC is actually installed now. Compile that and run it. So what will happen? We just enter something. Hello. It prints it back out. Right. So what's happening here? As the user enters something, so I'll say I entered hello here, the stack starts to get filled up. So 0 will have the H, E, L, L, O in all of the different locations within this words array. Now, what if I enter something longer than 10 characters? So the key here is this buffer, this array, should be able to hold 10 characters, right? What happens if I enter 1, 2, 3, 4, 5, 6, 7, 8 things? We're good. 1, 2, 3, 4, 5, 6, 7, 8, 9. Still good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that looks a little different. I got this abort trap 6 on my Mac here. Something's not quite right? So it finished out that function. It printed out all those A's, but something else is going on here. Now, if we take a look at the slides, if I entered A, B, C, D, E, F, G, H, I, J, K as an example, it fills up all of those locations, but there's nothing in the program, nothing in the compiler that prevents me from entering more than 10 characters, or actually technically more than 10 characters. And what happens is the computer just keeps on going. It keeps on writing to the stack. So when I give scanf words, it's really just giving the base address here where this location is, and it just fills it up with whatever comes next. So the A, B, C, D, and the whole alphabet onto K, and this return address that used to have some memory address now has this K in there. So after this function is complete, and in my code here, after we print it out, we do a return, and it's going to look for whatever this return address is, and it's going to try to go to the memory location of K. That's not a thing. That doesn't work, and that's where we get issues. That's where things start to go haywire here. So that's a problem, right? This is why buffer overflows are bad. We overflow that space, especially on the stack here, and we start overwriting into something else, right? Doing it on the stack, doing it in a place where I can overwrite that return address, that's where it becomes really, really dangerous. Even if you are overflowing buffers that are maybe not necessarily, or you're not getting to the return address, you're still overwriting some other data in some other location in memory that was not allocated for you, right? Or was not allocated for that specific variable. So this is another example. This one is a function that says check authentication. What this function's doing, so if we read through the code here, it has a parameter of password. So char star password, that's essentially an array that is a password, so a string. So I have this local variable called auth flag, this local variable called password buffer, and password buffer is 250 characters long, so that might be important. Now, if I do a string copy, so string copy is a kind of a dangerous function because I'm just going to copy whatever password is pointing to, all willy-nilly, into this password buffer. So if password is less than 250 characters, that will fit, right? If password is more than 250 characters, String copy doesn't care. It's going to copy the whole thing into password buffer. What we're doing to copy it into password buffer here, it seems like maybe an unneeded step, but that's to demonstrate the vulnerability. I could do just a scanf here in this function and read into password buffer as well. But then what happens in the rest of this program here, or this function, in that if statement, so we see a string compare for password buffer and password 1 exclamation point. So if whatever is in password buffer matches password 1 exclamation point, then I change auth flag to 1 to say that this user is authenticated and they got the password right. Right? That makes sense how that function works, I hope. If you have questions, let me know. I'm happy to explain it again or different. But basically this function, again, we're trying to check if the password is password 1 exclamation point and set that auth flag if it is. Now, how could we take advantage of this? Well, if we look at it on the stack, very top, we have that password address, which is a parameter. We have the return address, we have auth flag, and we have a password buffer of size 250. Now, we could just overwrite this password buffer with something that's much, much larger than 250, and it would overwrite that return address as we saw, right? But what if we overwrite it a little bit more selectively, I'll say. So if I had or put in a password into password that was maybe not just 250 characters, but the 250 first was the integer number 1. That drew terribly. We'll pretend that's a 1. It's kind of a 1. If I just make that 1 with a buffer overflow, I don't necessarily have to know exactly what this password of password exclamation point is, right? If you can figure out that it's using this auth flag and you could overwrite that auth flag, you could essentially get access without knowing the password. Yes, you could continue to overwrite and have even a longer password that would botch up this return address and kind of crash the program or take advantage of that return address. But you also could take advantage of that auth flag. So this is where buffer overflows are a problem. So how do you actually identify this buffer overflow thing? A couple examples here, and I'll have some more examples in a moment. String copy. We looked at that one already and saw in this last program or this last function that it was a problem, right? It's a normal function. It's a good, legitimate, useful function to copy one string into another, but you absolutely have to verify that the source string and the destination string are either the same size or the destination is larger than the source, that you actually have enough space in the destination to hold the string from the source, right? There's nothing inside of the function, inside of string copy, that will prevent an overflow. Instead of using string copy, we can use a different function called strncpy, which you'll see a lot of different functions with that n variable there. I'm going to see if I can pull up some documentation on that one and show you what that looks like. If you've never seen this website of c++.com, highly recommend it. Very good reference for all of these built-in functions. So this is in the string library. So strncopy says destination source and then the maximum number of characters to be copied from source. So with num, in this case here, let's do right here, strncopy. This is copying string 2 into string 3, but only 5 characters. There's no way I'm going to overflow it if string 3 is 40 characters. But if you know for sure the size of string 3 or the destination, if you know it's 40 characters, only copy 40 characters in, right? That's going to protect you and protect that program if you can limit to just the number of characters you actually need there. Gets is also a problem. So if you've ever seen that, actually if you try and use it in some compilers, it will not even let you compile. Or at least it will throw a warning and say, hey, this is bad. Gets is another function that we can use to get characters from standard input, kind of like we use scanf. With gets, there's absolutely no way to limit how much data is read in, right? same issue. We just read stuff all willy-nilly. And scanf with a %s actually will do the same. So that's not always going to be best either. Instead of getS and maybe scanf if we're reading in larger strings, to use fgetS, which also will have a parameter to specify length. So these functions will only read in a certain number of characters. So I want to take a little different approach at this again and look at another way that this actually can be an issue, that buffer overflows can be an issue. So if I have this character buffer here of size max buff, which is defined as 256, let's kind of take a look through the code and see what might be wrong here. If the length of input, which is the character array we're looking at, is less than max buff, then we'll do the copy. So instead of using strn copy like I just said, maybe this is a way that we can use string copy correctly, right? So if the length of the input is less than the size of the character array that we're putting it into, then it's fine to do the copy, and that is correct, but this is not implemented properly, right? So what's going to happen here, or what could happen here, this strlen function right here returns a variable that is of type size t. And size t is an unsigned type. Now we learned about signs, we learned about integer overflows last week, and this is going to make a big difference here. By default, if we don't say something is unsigned, it is signed by default. So length here is a short, and it is signed. What could happen here is strlen that is going to return an unsigned size t, which would essentially be an unsigned integer, try and store that in a signed short. That is a mismatch there. So I might be truncating the length that strlen would calculate when I'm storing that into len, and the number would actually be smaller. So if I have a large enough input that is of the correct size that it would truncate so that the truncated version is smaller than max buff, you could actually carry out a buffer overflow here. That would be a problem. And this is a buffer overflow in this example coupled with an integer overflow or integer underflow issue, right? So some other things to look for when dealing with buffer overflows or when trying to locate buffer overflows. Unsafe string handling functions. We covered a couple of those. getS, string copy, those are some pretty common ones. Scanf, in most cases, is even not the best one to use for some of these string issues. Use different functions that actually are safe for handling strings, that actually specify the size of the buffer that you're putting data into. Math used to calculate buffer sizes. We just covered that one, right? Make sure that math is correct. Make sure you cannot do any overflows or underflows with that math. Input from a source that could be tampered with. This is something that we've been seeing the entire time this semester, right? Anytime we're taking input from a user, from an attacker, from some place that could be controlled by an attacker, that's a place we want to look and make sure that data is being handled properly. Inputted data that is transferred to internal structures. So if we take any of that data from the user, from the attacker, and put it inside of something in a program, inside another string, inside of another array, something like that, that's another key place where we're going to look for these buffer overflows, right? If the attacker can try and put something larger into our program than our program can actually accept, then those structures, those variables can actually accept, that's where we get this buffer overflow issue. So how do we actually prevent this? Again, use those safe string handling functions. A lot of those are going to have that n in there, and also fgetS. You'll be able to define the size of the structure you're putting the data into, of the buffer that you're actually putting the data and information into, so you don't overflow that. Make sure you're looking at integer overflows when calculating sizes of these buffers as well, and that we're not having any integer overflows occur. And loops and arrays. When you're using arrays, make sure that you know the size and that your loops don't actually overrun those arrays. So if I have an array of size 10 and I try and run a loop over that array, but it goes beyond the end of that array, that's a problem as well. That's also another example of an overflow. And actually a small example of that here, this won't be working code necessarily. We'll try and make it kind of working code. So if I have a array, I'll say nums of size 10 here, and I say for I is equal to 0, I is less than or equal to 10, I plus plus, and I do something with that array, I'll say nums I equals I, and we're just assigning numbers into that array. There's actually an overflow issue here, right? So hopefully you can identify it. If you haven't yet, kind of pause the video and take a moment to inspect this and see what's wrong with it. So what's going on here, I have this array of size 10, so the indexes in that array will go from 0 to 9, but this for loop right here will go from 0 to 10, right? Since I say less than or equal to 10. Just that equals. That's my biggest issue. And that actually is the issue that's causing an overflow here. So when I'm going through this loop, nums is trying to overwrite the next location with 10. And that's a problem, right? Because what comes after this nums array, I don't know. It could be the return address, and I'm trying to overwrite the return address with 10, right? In any case, it's an overflow, and you're going too far. So that's the loops and arrays. Make sure your loops don't overrun your arrays. Anytime you're dealing with arrays, you're staying within the bounds of those arrays. So that's going to do it for this video. If you have any questions, let me know on buffer overflows. Otherwise, we'll talk to you in the next video.